At first, it is barely noticeable among the millions of points of light that crowd the sky. This area of space is far from dark, illuminated as it is by the light of 1,000,000 stars, crowding 100 million times more densely than they do around the Earth. A central cluster of suns wheel around at an incredible pace, spiraling towards a singular static point of light, the center of their and every other star's orbit. And it is here where the oddness of this central body begins to reveal itself. Instead of a smooth circle of light in the crosshairs, the object appears as a vast glowing ring, cross-cut just below the equator, filled at its center by a black, deeper even than the surrounding nothingness. And it is now you realize this is the black hole. But it is not just any black hole. This is the supermassive black hole at the center of our galaxy, Sagittarius A star. Up to this point, you have been propelled towards this curious body under your own power, but there now begins a subtle tug towards it. You find yourself in an orbit around its middle, along with a glowing band of accreting material which is lensed into a halo by intense gravity. Within the accretion disk, you're pounded and pummeled by fast-moving gas, dust and debris, and intense frictional heating causes the entire disk to radiate at high energy, blasting your body with X-rays and gamma rays. Your DNA is damaged beyond repair. But soon, that won't matter. It is at this point, reality starts to strain. From the perspective of a distant observer, the closer you approach to the inner edge of the disk, the slower you seem to fall. But as far as you're concerned, time is passing normally. Now, even if you could escape, everyone you know and their distant descendants are already dead. And it isn't just time that warps. Assuming you approach the black hole's gaping maw feet first, then your lower body will be experiencing a stronger gravitational pull than your head. Your entire body begins to distort, although the effect isn't as severe as it could be. A supermassive black hole like Sagittarius A star only has a moderate gravitational gradient compared to their smaller, stellar counterparts. This continues until, after an observer's eternity, your feet, hips, and finally head cross the event horizon. Passing this point is the end of your time in the wider universe. Beyond the event horizon, the gravity is too strong to let light or any signal you may survive to send escape. You are shut off forever. Inside, everything is turned on its head. Time and space trade places, and beyond the event horizon, it is time itself that pulls you down towards the center. No force in the universe can stop this, just as nothing can stop the flow of time itself. What you experience inside, no one can say, and certainly not you. Even if, impossibly, you survived irradiation, spaghettification, and the aging of the universe, then your voice would be forever silenced by gravity itself. All that is left is the slight mass increase of the Leviathan that consumed you, a mass increase that will only help your captor pull in more victims. Such is the fate of anyone or anything unlucky enough to fall into the mouth of a black hole. First mooted in 1783, the incomprehensible horror of these ultimate galactic predators has captured the imagination of scientists and pushed the boundaries of science for decades. Indeed, the supermassive variety are thought to reside at the center of every galaxy, and may well be the agents of their creation. While black holes can bring about ultimate destruction, their supermassive counterparts can also feed and fuel the very stuff of stars, planets, and life. But many of these supermassive black holes also leave us with a mystery. Just how did they get so big in the first place? If they are the seeds of galaxies, then what were their seeds? And finally, when, and indeed what, were the first black holes? Isaac Newton rarely went to sleep before 3 a.m. and worked 18-hour days. This worked for him. It won't work for you. It's hugely important to have a healthy routine, and a great way to overcome the initial inertia is trying out Fabulous, the #1 self-care app to help you build better habits and accomplish your goals, and the sponsor of this video. With a community of more than 30 million users, Fabulous is a digital coach that uses methods taken from evidence-backed behavioral science to help you develop great habits. It will help you create rituals and reminders throughout the day that will push you towards your goals step by step, little by little, from the first moment you wake up. Personally, I'd been hoping to increase my mindfulness and live a calmer life, and Fabulous's great systems have helped me stick to my goals and not let them drift away. And with Fabulous Premium, you can build and improve an unlimited number of habits and routines, unlocking all programs and exercises. So, start building your ideal daily routine. The first 500 people who click on the link will get 25% off a Fabulous subscription. Thanks to Fabulous for supporting education on YouTube. Rain clatters harshly on the tin roof of the rudimentary shelter. It is channeled down and collects into the growing gutter of water that winds its way through the muddy trench and past the sodden boots of the young soldiers who huddle for warmth beneath the darkening December sky. The gunfire and shelling has mercifully stopped for now, and the senior lieutenant ducks inside the little refuge to turn his attention to the pile of dispatches on the desk. It is 1915, on the Eastern Front of World War I, and the lieutenant is Carl Schwarzschild. Schwarzschild is an accomplished theorist and mathematician, and the director of the Astronomical Observatory in Potsdam. Even so, the relentless pressures of the Great War see him sign up for the war effort and squat in his greatcoat alongside the harrowed soldiers of the German army. But tonight, his attention is caught by a familiar handwriting on the wrappings of a bulky envelope. Instantly, he recognizes it as the hand of his friend and colleague, Albert Einstein. Entitled The Field Equations of Gravitation, the paper within lays out the mathematical basis for what will become known as the general theory of relativity, and all of our modern understanding of gravity on cosmic scales. Incomprehensible to all but the most involved theorist, it describes in elegant formulae how matter causes spacetime to curve, and how spacetime tells matter how to move. Schwarzschild holds the paper in trembling hands, and that evening risks a dim and flickering electric light to read and study Einstein's work with delight. The circular reasoning of the scholar's equations may be mathematically elegant, but this also makes them notoriously difficult to solve. Schwarzschild, though, is grateful for the distraction, and just a matter of days after receiving Einstein's supposedly impenetrable formulae, he writes to his friend, offering the unthinkable: a solution. In the covering letter, Schwarzschild writes, "As you see, the war treated me kindly enough in spite of the heavy gunfire to allow me to get away from it all and take this walk in the land of your ideas." What Schwarzschild saw on this relativistic walk was a surprisingly simple solution, which completely describes how space-time is curved around a spherical object like a planet or a star. By extension, he showed how it becomes much harder to escape the gravity of a small, compact and highly dense star, and that by pushing the limits of density and shrinking the star even further, the curvature becomes so great that no particle, not even the photons of light, can escape. The distance from a given point at which nothing could escape, which would come to be known eponymously as the Schwarzschild radius, depends on the universal gravitational constant, the speed of light, and the amount of mass that is concentrated in one place. Since both gravitation and the speed of light are constant, the Schwarzschild radius really only varies with the mass. The more mass, the further the radius extends. For instance, the Schwarzschild radius around a human is around 1/millionth the diameter of a single quark. So, if you were to be condensed down into this size, the gravity would be enough to trap you there forever. Around the Earth, it is around 9 millimeters, the Sun, 3 kilometers. Of course, since the actual sizes of these bodies far exceed their Schwarzschild radii, their mass isn't concentrated within it, and so we see no bizarre phenomena. It is only in the cases of extremely dense objects, Schwarzschild reasoned, that this extreme space-time curvature would have any tangible effects. Schwarzschild himself survived the gunfire, but soon after succumbed to a skin disease he contracted while on the front. He didn't live to see how his ideas would be developed further. Indeed, at the time, many physicists denied that such an impossibly dense object and its associated space-time curvature could really exist. In 1964, 2 Geiger counters were launched above the atmosphere in a short rocket flight in order to search for celestial sources of X-rays, which are normally blocked by our thick blanket of air. These instruments swept across the sky and pinpointed one such intense X-ray source in the constellation of Cygnus, which became known as SIG X1. Puzzlingly at the time, the bright X-rays didn't seem to correspond with any significant star or body that could be seen, and for several years SIG X1's true nature was a mystery. But later, more precise measurements offered additional evidence to astronomers' growing suspicions. The source's very fast X-ray variability on timescales less than a second suggested that the X-ray emitting region was much smaller than your typical star, and the discovery of a binary companion allowed the mass of the source to be calculated from the size of the companion's orbit. The result was stunning. SIG X1 was smaller than a star, but some 15 times more massive. It far surpassed the theoretical limit for white dwarfs or neutron stars, leaving Schwarzschild's light-swallowing singularity the most likely solution. As the mysteries of SIG X1 unraveled throughout the early 1970s, science had also coined a new name for this gravitational monstrosity. John Wheeler, an American theoretical physicist, took it upon himself to revive interest in the general theory of relativity after World War II. And in a lecture at NASA in 1967, an audience member, sick of hearing him drone the words gravitationally completely collapsed object for the umpteenth time, suggested black hole as an alternative. Wheeler seized upon this simple and evocative term. From that moment forward, black holes became the common, even household name. Today, we have a good understanding of how certain black holes like SIG X1 come to be. Stars burn hydrogen and helium fuel until that fuel is exhausted, at which point the heat generated from fusion is no longer great enough to sustain them against the gravity that wants to pull their matter in on itself. If the mass of the dying star is more than about 3 times that of our Sun, then theoretically, there is no force that can stop it collapsing completely in. Much of the outer shell of material may be exploded outwards in a dramatic supernova, leaving behind an extremely dense remnant that curves space-time, just as Carl Schwarzschild predicted. This remnant is surrounded by an event horizon, a point of no return which marks its new boundary, the edge of the so-called hole, which lives on to swallow any luckless matter that passes its way. The more matter it swallows, the larger it gradually grows. But still, the region inside the event horizon remains a mystery. Einstein's equations suggest that time itself is destroyed at the center, and some scientists have even suggested that the singularity actually leads to another universe altogether. But there is no way we can find out, no experiment we can perform. As nothing can travel faster than the speed of light, nothing is powerful enough to escape the event horizon. Inside this impenetrable boundary, defined by the Schwarzschild radius, everything is unknown. Nevertheless, the process by which so-called stellar black holes form is reasonably well understood, and astronomers suspect that some 100 million are lurking in our galaxy alone. But their small size makes them hard to find, and to date we have detected only a dozen or so of these black objects in the blackness of space. But they do have siblings. Siblings that lurk at the hearts of every galaxy. Siblings that are much more conspicuous but at the same time, much, much more mysterious. April the 10th, 2019. A picture sweeps the globe, instantly becoming a viral sensation. Unlike most viral images, this one wasn't visually impressive on its own. It was fuzzy and indistinct, an orange torus on a plain black background. But it nevertheless represented the work of hundreds of scientists over half a decade. Just a few weeks later, more than 1 billion people had laid eyes on the very thing that physicists had refuted for years, and which most astronomers never expected to see directly outside of their imaginations. It was, of course, the first ever image of a black hole. Black holes, as their name and very definition dictate, are black. At first glance, this makes the prospect of photographing them seem like a fool's errand. But scientists have seized upon the voracious nature of these gravitational chasms and their effects on the matter that surrounds them. A sufficiently massive black hole, surrounded by a sufficiently large disk of gas and dust, theoretically gives off enough radiation in the form of high-frequency radio waves to be detected by a sufficiently large radio telescope. Here on Earth, these black holes needed to be more than massive. They had to be supermassive. The name for a black hole that weighs millions, or even billions of times that of our Sun. Astronomers believe that these leviathans reside at the center of most large galaxies, and indeed may be crucial to the formation and evolution of the galaxies themselves. As they feed and grow, the supermassives occasionally spit out accelerated globs of gas, counterintuitively helping stars to form just at the moment of others' death. The link is so strong that some astronomers have begun to grapple with the question of which came first. Did the earliest galaxies feed and fuel supermassive black holes, or did the supermassives, already in existence, somehow seed the stars and galaxies of our modern cosmos? So, in searching for the ideal supermassive candidate, the black hole imaging scientists needed only to turn to the heart of our own Milky Way. Here, the supermassive black hole, known as Sagittarius A star, looms, 25,000 light-years away from Earth, with a mass of some 4 million suns. Its relative proximity may have made it an obvious target, but that nearness also brought with it additional problems. Embedded as it is within the milky streak of stars that give our galaxy its name, there are countless celestial objects blocking a clear view of the supermassive black hole. Not only that, but as the Earth turns, so the center of the galaxy sweeps across the sky each night, it would be very difficult to maintain a telescope fix for long enough to gather the necessary data. Therefore, to begin with, the international team of scientists set their sights on a more distant supermassive, this time residing at the center of the Messier 87 galaxy in the Virgo cluster. At first, this may seem odd. M87 is some 55 million light-years away, far further than the mere 25,000 light-years to Sagittarius A star. But its sheer size made up for the distance. For M87 weighs an incredible 6.5 billion times our Sun's mass. Also, at such a distance it stays relatively still in the night sky, and there is a clear line of sight all the way. The next challenge, however, was to actually build a telescope that was big enough to reveal M87's blackened core. In radio astronomy, the resolution of the final image obtained depends on the size of the telescope aperture that collects the radio light. This means that for small and distant objects, bigger is always better, leading to some fairly on-the-nose names for modern high-resolution radio telescopes. The giant Ukrainian radio telescope, the large millimeter telescope, the very large array. But for M87, even very large was not large enough. The radio telescope would have to be roughly the size of the entire Earth. And so, researchers worldwide collaborated to connect 8 radio telescopes from across the globe, forming a composite telescope with an aperture that spanned from the South Pole to Spain and a resolution around 4,000 times better than the Hubble Space Telescope. This so-called Event Horizon Telescope, with its component parts synchronized by atomic clock, collected radio waves from the direction of M87 for 4 days in 2017. The observations from each monitoring station were delivered on physical hard drives, since internet speeds were unable to cope with the volume of data. 2 years of intensive data processing later, and the team finally had their impossible image. A silhouette of the M87 Supermassive's black hole event horizon, lit by the radio light of its accretion disk. But the discoveries didn't stop there. In May 2022, after an additional 3 years of processing, data from the Event Horizon Telescope's initial observations of the Milky Way were finally resolved into the second ever image of a black hole. We finally caught a glimpse of the beating heart of our own galaxy, Sagittarius A star. Imaging and analysis continues to break new ground in visualizing and understanding these supermassive black holes, but there are still so many unanswered questions surrounding their lives and, crucially, their formation. Just how does a black hole get to weigh as much as M87 does? Or more? Indeed, 6.5 billion times the mass of our Sun doesn't even come close to the largest black hole we've found. TON 618, belonging to a quasar 10.4 billion light-years from Earth, tips the balance at an incredible 66 billion solar masses, making it a so-called ultramassive black hole. It alone is heavier than all the stars in the Milky Way combined, and with accretionary winds that reach 20% the speed of light, it consumes matter at such a rate that its luminosity exceeds that of all the stars in its galaxy. When astronomers detect quasars, the brightest objects in the universe, they are detecting these super or ultramassive black holes within active galactic nuclei. They are arguably the most impressive single objects in the entire cosmos. But how did they form? Some suggest that these heavyweights started out just as their stellar black hole cousins. A gigantic star lived, died dramatically, and left behind a bulky black hole in its wake. Then, over a period of billions of years, that gravitational titan got lucky, encountering star after gigantic star to feed its insatiable hunger, growing gradually until it attained mammoth proportions and ensnared entire star systems into stable orbit around it. But critics fail to see how such growth could be accomplished by gradual means alone, and suggest a much more staggered approach. Instead of a single voracious beast consuming stars and gas, alternative theories see supermassives born in mergers between several smaller stellar mass black holes. Indeed, such mergers have already been observed by the gravitational waves that ripple out from them. It would certainly be a shortcut to acquiring mass, but questions remain as to how likely these binary black hole encounters are. Perhaps our continued observation of the supermassive black holes in our galactic neighborhood will help to answer these questions. But there is one overarching mystery that stands regardless. When we peer back into the distant and consequently ancient cosmos, we still find supermassives. The ultramassive black hole TON 618 is nearly 11 billion years old, and many supermassive black holes have been detected dating back to just a few million years after the Big Bang. So, if they assembled gradually, or through repeated mergers of stellar black holes, their presence so soon in the cosmological timeline implies that innumerable stars have already lived and died to form them. And here is where the problem lies. Plugging in the masses of these early supermassives and the well-constrained estimates of star formation in the earliest phase of stellar growth, these supermassive black holes just shouldn't be possible. Some giants had grown to 1 billion times the mass of our Sun by less than a billion years after the Big Bang, but calculations show that only 100,000 solar masses should be possible, a difference of 4 orders of magnitude. There is another phenomenon called a direct collapse black hole that could offer at least a partial explanation. Instead of forming during the death of a star, as with stellar black holes, direct collapse singularities form, as their name suggests, directly from the collapse of material in the early universe, but without any intervening star formation. Such early, high-mass black holes could be the beginnings of the supermassives we see today, but they probably aren't the ultimate solution. The conditions for their formation are so restrictive that they were likely rare phenomena, and not enough to explain the supermassive shepherds and their galactic herds that fill the universe today. There must be another piece to the puzzle. Lurking back at the dawn of time, there must be something that helped to feed these giants from their birth and help them to grow into the black behemoths that power our galaxies today. But what could create a black hole before stars are born? When a 20-year-old undergraduate student first fell down the stairs in Oxford in 1962, his doctors helpfully told him to lay off the beer. But when this clumsiness continued into the next year, his family began to worry, and the young scholar was sent to hospital for a series of tests. After 2 weeks of rigorous investigations, the physicians still didn't tell the young man what was wrong with him, except that he was an atypical case, and they expected it to get worse. Reluctant to ask for more details, the young Stephen Hawking simply took the vitamins the doctors recommended, even though he could see in their eyes that they didn't expect them to work. By this time, Hawking had begun his postgraduate studies at the University of Cambridge. The medical diagnosis he had avoided facing was one of amyotrophic lateral sclerosis, or ALS, which sees the motor neurons in the brain rapidly degenerate until you're no longer able to coordinate your movements, talk, and eventually swallow and breathe. The doctors predicted that 21-year-old Hawking had 2 years left to live. But Stephen Hawking defied his doctors. Instead of fading away over the next 2 years, he took his vitamins and kept fighting for 55 years more. In refusing to surrender to his ALS, Hawking completes his postgraduate studies, becomes an esteemed academic, and eventually a household name. Arguably one of the most famous scientists of all time, rivaling the great Charles Darwin and Albert Einstein, and becoming one of the youngest ever scholars to be elected a Fellow of the Royal Society. And yet, to the public, many of whom failed to grasp the nuances of his physics, he became defined by his ALS and his tenacity in overcoming it for so long. But his science was truly worth the accolades and fame he received, for during his long and fruitful academic career, Hawking transformed our understanding of the universe's beginnings and black holes. His doctoral thesis, completed in 1966 under the shadow of his recent diagnosis, focused on the debate that raged at the time concerning the beginnings of the universe. Inspired by the novel physics of an impossibly dense point at the center of black holes, Hawking made a similar suggestion for the beginning of the universe itself. Throughout the early 1970s, he described and defined the fundamental rules for black holes, including the observation that an event horizon could never get smaller. Later, however, he attempted to unite the fundamentally incompatible theories of general relativity and quantum mechanics to postulate the existence of a kind of radiation that could actually see black holes evaporate and eventually disappear. This Hawking radiation, as it became known, was a phenomenon that held up in theory, but had not been seen in practice in any discovered black hole. Hawking continued to grapple with these problems throughout his entire academic life. But even while he was tackling the unknowable about modern black holes, Stephen Hawking's attention was continually drawn back to the cosmos as a whole, and in particular, its beginnings. Hawking's study of black holes endlessly informed his research into the unreachable Big Bang, and his unique understanding of the universe's first moments gave him new insights into black holes. And so, in 1971, he popularized a radical suggestion for which, at the time, there was little tangible evidence. He proposed that a new type of black hole could be found at the beginning of the universe, a so-called primordial black hole which formed not from dying stars, but from the birth of the cosmos itself. 13.8 billion years ago, the Big Bang results in the creation of energy fields that permeate the cosmos and which, as the universe cools and expands, disentangle into the fields of force that rule our lives today. Further cooling sees the very first subatomic particles, quarks and leptons, spring into existence and be endowed with properties like mass and charge, which will, again, come to rule the physics of the next 13.8 billion years. But the universe is still far too small, hot and turbulent for any real matter as we know it today to exist. Suddenly, inflation, triggered by as yet unknown forces, sees the universe double in size around 90 times in 10 million billion billion billionths of a second. Tiny variations in quantum energy throughout the minuscule pre-inflationary universe are now almost instantaneously transformed into vast regions of inhomogeneity. All over this inflated universe, there are variations in the density of particles and energy that will provide the seeds for the overall structure of the cosmos many billions of years later. But Stephen Hawking also foresaw another consequence of these density variations over newly expanded space. Where there is stuff, there is gravity, and these denser regions begin to curve the fabric of space-time on a macroscopic scale for the very first time. According to Hawking, the response to this sudden and spontaneous shift was for the denser patches to begin to tumble into their own gravitational wells, collapsing in on themselves due to gravity and in doing so exponentially increasing their own gravitational potential. As this runaway gravitational collapse continues, the fundamental stuff of the universe is compressed into the mathematically infinitely dense singularity which captures all. The singularity is cloaked in an event horizon and the newborn particles are locked away for eternity, before spending even one full second in the universe. All over the freshly expanded cosmos, primordial black holes appear at the hearts of the densest patches of nascent matter. Mathematically, there is only a very brief window after the Big Bang in which the primordial black holes could have formed. When the universe has reached 1 second old, expansion and cooling has already rendered the cosmos too large and too calm to allow spontaneous gravitational singularities to appear. But prior to this point, there is no physical reason why primordial black holes couldn't have filled the embryonic cosmos. Hawking and others calculated that the later in this 1 second window that the gravitational collapse occurred, the larger the primordial black hole would be. This means that they could range in size from anywhere from 1/100,000th the mass of a paperclip up to 100,000 times the mass of the Sun. But here lies the problem. Like so much of Stephen Hawking's work, his elegant mathematics are watertight, but it leaves us with little in the way of testable hypotheses. How do you go about proving that primordial black holes did or didn't exist? We must find a way to detect them, or at least detect their tangible effects on the early evolution of the universe. But when we don't know how numerous they were, exactly when they formed, and exactly what size they're likely to be, then searching for the earliest black holes is tantamount to finding a needle in the cosmological haystack. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. The 8 major planets of our solar system. Some have been observed since the 2nd millennium BC, seen and studied with the naked eye. Others have been spotted by telescope or predicted based on their effects on other objects and subsequently discovered right where we expected them to be. But there may yet be one more object left to find. Even after 4,000 years of astronomical study, there are mysteries lurking on our celestial doorstep. In 1951, Gerard Keiper, an astronomer and professor at the University of Chicago, contemplated a cometary conundrum. Scientists had long observed so-called short-period comets, icy bodies which swing through the solar system on elongated orbits, passing close to Earth and the Sun every 200 years or less. Halley's Comet, which was last visible to the naked eye in 1986 and will revisit us again in 2061, is one such visitor, but its flybys won't last forever. Every time the comet passes close to the Sun, it evaporates more of its icy core, and after a few more orbits it will be lost completely to nebulous interplanetary space. But by this reasoning, after the 4.5 billion years that our solar system has been around, there shouldn't be any more short-period comets left. Unless, Keiper reasoned, there was a nursery of icy bodies far out in the outer solar system, beyond the orbit of Neptune. A belt filled with orbiting chunks of ice could be disturbed by the gravity of Neptune and the other giant planets, flinging ice blocks in towards the Sun to become comets on a swinging death spiral that lasts thousands or even millions of years. Despite Keiper's early predictions, it wasn't until 1992 that evidence for this belt of icy objects was actually discovered. NASA scientists spotted the first one and then many more of these so-called trans-Neptunian objects, and the space they occupied became known as the Keiper Belt. But as the inventory of Keiper Belt objects grew, another conundrum presented itself. There were some that seemed to behave quite strangely. One, a dwarf planet named Sedna, discovered in 2003, has a very long, extremely elliptical orbit that takes more than 10,000 years to complete. And even at its closest approach, Sedna is still 2.5 times further from the Sun than Neptune. There is simply no way that Neptune could be responsible for setting off this huge motion. Other extreme trans-Neptunian orbits also show a surprising pattern, clustering to one side of the solar system and tilted deeply below the equatorial plane. Statistically, such a distribution is extremely unlikely. In the absence of external influences, these objects' orbits should randomize over 100 million years. And so, in 2012, a Brazilian astronomer named Rodney Gomes suggested an explanation for these bizarre orbital patterns. That there was in fact an external influence in the form of a distant, massive planet that shepherds them around. That hypothetical planet has come to be known as Planet 9. By the orbital calculations, Planet 9 would be around 6 times the mass of the Earth, travelling on an elongated and tilted orbit around 400 times further from the Sun than the Earth's own orbit. But despite knowing this, and searching specifically for it with the highest resolution instruments we possess, astronomers haven't found a trace of this Neptune-sized planet. Critics have countered that the anomalous orbits could be the result of observational bias, shaped by how and where we can search for Kuiper Belt objects, and that Planet 9 doesn't really exist. Jim Green, NASA's chief scientist at the time, quoted Carl Sagan, saying, "Extraordinary claims require extraordinary evidence." And there is another tantalizing possibility, another even more extraordinary claim. What if Planet 9 has all the characteristics scientists have calculated, the mass, the distance, the orbit, but is something much, much smaller? The first detected primordial black hole. To begin with, positing a black hole instead of a planet would help to explain why this gravitational shepherd has been so difficult to detect. With a mass equivalent to 6 Earths, a gravitationally collapsed black hole's event horizon would be approximately the size of a tennis ball. Not only would it be completely black, but set against the vastness of space, it would be almost impossibly tiny too. Of course, theorizing primordial black holes in our galactic neighborhood is one thing. Actually detecting these tiny but potent objects is quite another. Some suggest that their intense gravity would be enough to attract a micro-halo of dark matter, just as entire galaxies are thought to be enveloped in a dark matter halo on a massive scale. So, by searching for the dark matter and its associated radiation in the direction of Planet 9, we might hope to distinguish planet from black hole, and in doing so provide evidence for the early evolution of the universe itself. And yet, this methodology depends very much on the theoretical assumptions of what exactly dark matter is and how it behaves, which is by no means resolved. Dark matter is so named because, although it makes up some 27% of the universe as a whole and outweighs normal matter by some 6-1, we have never been able to detect it directly. It is dark, invisible to every instrument we have yet invented. Two camps suggest two different options for the identity of dark matter: WIMPs and machos. WIMPs, or weakly interacting massive particles, are a subatomic particle that interacts with the universe via gravity, but does not otherwise fit into the standard model of particle physics. On the other hand, machos are massive astrophysical compact halo objects, and are theorized as heavy astronomical bodies that could explain the gravitational effects in dark matter halos. Stephen Hawking himself was among the first to suggest that the primordial black holes he predicted could be a type of macho, thereby making up some, if not all, of the missing matter. If so, the dark matter that holds the universe together is not only dark because it is unknown, but because it is dark by its very essence. Primordial black holes become tiny pinpricks in the fabric of space-time, which, when clustered around galaxies, help to keep swarms of billions of stars in check. The combined mass of primordial black holes formed in the first second of the universe could be enough to outnumber normal matter. It is perhaps a sobering thought that possibly only a sixth of matter that came into existence at the birth of the universe escaped immediate imprisonment behind an eternal event horizon. How then would you detect a primordial black hole? One toolkit depends on another of Stephen Hawking's predictions: Hawking radiation. This is thought to be produced at the event horizon of all black holes when quantum particle interactions are subjected to general relativity. The result of this is that black holes emit a kind of gamma-ray glow and will shrink over time as they undergo something like evaporation. Not only that, but Hawking predicted that the smaller a black hole's event horizon, the faster it will evaporate, leading to an exponential emission that ultimately produces an explosion. Any black hole that was less than 10 to the power 11 kilograms in mass would be expected to decay on a timescale shorter than the age of the universe, so we could search for their swan songs across the night sky. The Fermi Gamma Ray Telescope, which has been circling our planet in low Earth orbit since 2008, is well equipped to search for these gamma ray explosions, but the results of nearly 15 years of observation have not been promising. And here is a key piece of evidence, or lack thereof. The absence of Hawking radiation outbursts suggests that, statistically, less than 1% of dark matter could be composed of these tiny, primordial black holes. There is always the possibility that Stephen Hawking's theory was somehow incorrect, and that Hawking radiation and the associated explosions don't actually occur. Indeed, the conclusions are based on a mathematical house of cards with no robust data points to glue anything in place. But other possible detection methods are rooted in more traditional orbital mechanics and observed phenomena. The Fermi Gamma Ray Telescope has the ability to search for gamma rays from other sources, not just from potential primordial black holes. If those gamma rays from, say, pulsing neutron stars or supernovas flicker unexpectedly, then this may be due to gravitational lensing as a primordial black hole passes by. Still, however, the results are not promising. Both gamma ray and optical astronomy have failed to find convincing evidence of any black hole flybys, and the statistics based on the duration of the survey and number of candidate discoveries puts a limit on the numbers of primordial black holes out there that weigh a certain amount. And based on this, it's very unlikely that Earth-size or smaller black holes are the hidden machos that make up dark matter. Other clues have been sought but are similarly lacking. It's expected that the gravitational wells of wandering primordial black holes would be able to capture other dense objects like neutron stars and white dwarfs, leading to their ultimate destruction. But the fact that these stars still exist in great numbers puts yet another limit on the possible number of primordial black holes that have been hanging around for the last 13.8 billion years. Even probing the cosmic past for traces of these early phenomena leaves us wanting. The existence of primordial black holes so soon after the Big Bang would have led to an accretion of matter early in its history. Early enough that it might be expected to create recognizable signals in the pattern of the cosmic microwave background radiation. But analyses of that universal scale fingerprint reveal no signposts to early black holes, at least those between 100 and 10,000 times the mass of our Sun. If they existed, then they were too small to leave a scar. Since Stephen Hawking first popularized the idea of primordial black holes in 1971, astronomers have tried to think outside the box to try and find ways to verify or refute his hypothesis. For the most part, they have yielded little in the way of positive results, and for a time, the future of primordial black hole theory looked bleak. That was until 2015. When the brand new LIGO instrument in the United States detected gravitational waves that were traced back to the collision of two black holes, each with a mass 30 times that of our Sun. This detection alone was exciting and confirmation that gravitational waves were not only real and detectable, but could also be a useful tool in probing the distant universe. But the implications of what they'd found had black hole scientists excited for an entirely different reason. Black holes with 30 solar masses are too big to have been formed by conventional stellar death, and yet they are too small to be explained by supermassive black hole mechanisms either. Is there another possible explanation? Primordial black holes could very well be it. If most primordial black holes had a similar mass, then calculations of how often they would meet and collide seem to match the frequency of collisions now being detected by LIGO. And so, finally, a measurable result seems to be breathing new life into the old black holes. The earlier negative results hadn't altogether ruled out the possibility of primordial black holes, but rather put strict limits on what masses they're likely to be. Such limits probably rule them out as the sole source of the universe's dark matter, but the case on their formation and influence is by no means closed. And the mass ranges that still haven't been explored by current observational techniques do offer a tantalizing possibility. Indeed, simulations that replace all of the assumed dark matter with primordial black holes of 1.4 solar masses show us that they could play a major role in the early evolution of the universe, including seeding the first stars, galaxies, and supermassive black holes. The question of whether, when, and how primordial black holes formed and evolved in the first second of the universe is still one of the biggest mysteries in cosmology today, and a topic that continues to attract speculation and experimentation. Scientists' hopes lie in the newest and most advanced instruments, such as the James Webb Telescope, which will image the earliest stars and galaxies and attempt to corroborate theories of primordial black hole seeding, or LISA, the Laser Interferometer Space Antenna, a space-based gravitational wave detector planned to launch next decade, which may be able to search for ripples from black hole mergers of likely primordial size directly. There is still much to learn about the first black holes, but as Stephen Hawking realized, understanding them offers the opportunity to unlock the secrets of the cosmos. Primordial black holes, if they do exist, may hold the key to our universe's earliest moments, the nature of dark matter, the driving forces between supermassive black holes, and the evolution of galaxies, stars, and ultimately, us. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.